Imagine trying to pack a suitcase perfectly. Too loose, and things break, but too tight, and you literally cannot close it. DeepMind just solved this packing problem for AI, and the results are faster and sharper than ever.
It really is a massive shift in how these models handle data.
Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik.
I am thrilled to dive into this one with you.
And before we really get going, I should explicitly state that both of us, your hosts, are AI-generated voices guiding you through this deep dive today.
That's right. And that suitcase analogy you just used, it's actually a surprisingly accurate way to frame what we are looking at.
Yeah,
We are discussing a paper called Unified Latents, or UL. It's subtitled How to Train Your Latents by Jonathan Heek and the team at Google DeepMind Amsterdam.
Unified Latents. It sounds, I don't know, very organized.
It does.
But from what I gathered reading through the source material, it's basically trying to fix a massive fight happening inside generative AI models right now.
Exactly. It addresses a fundamental trade-off in how we build diffusion models.
And those are the models behind things like Stable Diffusion or Midjourney, right?
Correct. The fight is essentially between image quality on one side and ease of generation, or learnability, on the other.
Okay, let's unpack this for everyone listening. So we know diffusion models generate images by reversing a destruction process.
Right. They turn static or noise back into a clear picture.
But they don't usually work on the raw pixels themselves.
No, working on raw pixels is computationally, well, it's incredibly expensive. An image has millions of pixels. So instead, researchers use what we call latents.
A latence, yeah.
Think of a latent as a compressed blueprint or like a shorthand summary of the actual image.
Got it. So instead of the AI trying to paint every single brick of a house from scratch, it just works with the blueprint?
Precisely. It's a much lower resolution, so it's way easier for the system to handle.
Yeah.
This is the whole idea behind the latent diffusion model approach. You have an encoder that shrinks the image down into this blueprint, and then a decoder that blows it back up into full pixels. But here is the major tension. How much detail actually goes into that blueprint?
Ah, okay, so this is the packing problem.
Exactly. Let's look at scenario A. You keep the latent, very simple, very low information.
Which sounds good for the AI generating it, right?
It's great for the generative AI. The rules are simple, so it's easy to learn and create new blueprints. But when you hand that super simple blueprint to the decoder to reconstruct the actual image, it's missing too much data.
So the final image looks bad.
Right. You get blurry textures, or the fine details are just totally gone because they weren't in the blueprint to begin with.
Okay, so that brings us to scenario B. We pack the blueprint with a ton of detail, high information content.
And the decoder loves that. It can reconstruct the image perfectly, sharp as a tack.
But now the generative AI struggles.
Exactly. The AI that has to dream up new images from scratch, it just can't figure out the patterns effectively because the blueprint is so incredibly dense and complex. It's too hard to model.
So you are basically stuck.
You are.
Either your image quality suffers or your generation capability suffers.
Yeah.
And the paper mentions that existing methods, like VAEs, the variational autoencoders, they require a lot of manual tuning to balance this out.
They really do. You end up having researchers manually tweaking these penalty terms, specifically something called the KL penalty.
Just trying to find a middle ground.
Yeah, trying to force the latent to be simple enough to learn but detailed enough to decode. It is a lot of guesswork.
And it doesn't always work.
No, you often get visual artifacts or something called posterior collapse, where the latent space just totally stops being useful.
Enter DeepMind with Unified Latents. They claim to have solved this trade-off systematically.
And they have done it by fundamentally rethinking the architecture, not just turning knobs.
Okay, before we get into exactly how they rebuilt the architecture, this is a great moment to pause and thank the people making this deep dive possible.
Absolutely.
This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
All right, so getting back to that DeepMind secret sauce.
Yes, Unified Latents. What is the actual framework here?
The framework connects three distinct components in a very specific, unified way. An encoder, a diffusion prior, and a diffusion decoder.
Encoder, prior, decoder. Let's break those down for the listener.
The first big innovation is in the encoder. Usually an encoder tries to learn a complex distribution of probabilities, which causes a lot of instability.
Right.
DeepMind simplified this. Their encoder predicts a deterministic latent, meaning a fixed value, and then it adds a fixed amount of Gaussian noise on top of it.
Wait, fixed noise. So they aren't letting the model decide how fuzzy the blueprint is?
No, they are not. And that is a crucial detail. They explicitly link this fixed noise to the minimum noise level of the prior.
Okay, you mentioned the prior. What exactly is that doing in this setup?
The prior is a diffusion model that lives entirely in the latent space. Its whole job is to model the blueprint itself.
Oh, I see.
Yeah, by fixing the noise in the encoder, they ensure the latent is always in a format that the prior can actually understand and learn from. It acts as a regulator.
So the encoder isn't just shouting into the void, hoping the rest of the system gets it. It's speaking a language the prior is guaranteed to understand because those noise levels are perfectly matched.
Exactly, it's a massive stabilizing factor. And then comes the third piece, the diffusion decoder.
Right, because usually in models like stable diffusion, the decoder is a GAN, a generative adversarial network.
Exactly, but DeepMind swapped that out for another diffusion model.
A diffusion model to decode. Why does that make a difference?
Because diffusion models are phenomenal at reconstruction. Even if the latent blueprint is heavily compressed, a diffusion decoder can naturally hallucinate those missing fine details to reconstruct a really crisp, high-res image.
So it completely handles that scenario. A problem we talked about earlier where simple latents led to blurry images.
Precisely. It picks up the slack.
Okay, so walking through the whole pipelines from start to finish, I put an image in. The encoder turns it into a deterministic latent and adds that specific fixed noise.
Right, and the paper actually mentions they use a log SNR of 5 for that noise.
Okay, log SNR of 5. Then the prior learns to predict that latent from the noise.
Correct.
And finally, the diffusion decoder takes that latent and turns it back into a high-quality, full-pixel image.
You have got it perfectly. And because of this specific structure, they introduce something incredibly useful for researchers. They call them loss factors and sigmoid bias.
Okay, loss factors and sigmoid bias, those sound a bit intimidating.
I know it sounds a bit heavy on the math, but just think of them as volume knobs for the byte rate.
The byte rate, like an MP3.
Kind of, yeah. Because of how they set this up, they can mathematically bound the bits per dimension.
Meaning they know exactly how much information is packed into the suitcase.
Exactly. It makes the whole system interpretable. Instead of the old way of just guessing and checking, they can tune these hyperparameters to explicitly control the information density.
Wow.
If you want a simpler latent because you are running a smaller model, you just turn the knob one way. If you have a massive supercomputer and want perfect detail, you turn it the other way.
That is huge for efficiency. But that brings us to something in the paper that really confused me at first, and I think it's crucial to clarify for everyone listening.
Oh, the stage 2 training.
Yes. The paper talks about a stage 2 training or a base model. I thought the prior was the thing generating the images. Why do they need another stage?
It's a nuanced point, but it's really the key to why the images actually look good to us. In stage 1, they train the prior using a scoring metric called ELBO, the evidence lower bound.
I remember ELBO. It's a pretty standard loss function in machine learning.
It is, but it has a major flaw when it comes to visual generation. ELBO tends to weight all information equally.
What do you mean by equally?
It cares just as much about tiny, imperceptible background noise as it does about the shape of a person's face.
Oh, that sounds incredibly inefficient. As humans, we don't look at microscopic pixel noise. We look at the faces and the objects.
Precisely. So if you generate images using just that stage 1 prior, they look technically correct, but perceptually a bit off. Not great.
So DeepMind does a stage 2 to fix that.
Yeah. They freeze the encoder and decoder, those parts are completely done, and they train a brand new base model directly on those latents.
And this base model uses a different scoring system.
Yes, it uses something called sigmoid weighting. This weighting explicitly focuses the model on the visual aspects that actually matter to human perception.
Okay, so it essentially tells the AI, don't worry about the microscopic static, just worry about getting the eyes right or the texture of the fur.
That is exactly what it does.
So the prior makes sure the latents are mathematically sound and stable, and then the base model swoops in to make sure the final output actually looks good to a human.
That is a brilliant way to summarize it.
All right, so let's talk results. Does this unified framework actually work better than the systems we currently have?
Significantly better. They tested this extensively. On ImageNet 512, which is a major benchmark, Unified Latents achieved an FID score of 1.4.
And just as a quick reminder for you listening, FID is basically the standard how real does this look score in AI generation, and a lower number is better. So 1.4 is really impressive.
It is highly competitive with the absolute best models out there. But what is even more interesting is the efficiency.
How so?
It requires noticeably fewer training FLOPs, or floating point operations, to get to that level of quality compared to models trained on traditional stable diffusion latents.
So it learns faster.
It learns much more efficiently, yeah. You are getting better quality for the exact same compute budget, and the reconstruction quality, which they measure with PSNR, is much higher.
Now, the paper took a bit of a shot at some other methods here, right? They specifically mentioned models relying on Dino.
They did, yeah. Methods that use pre-trained encoders, like Dino, they often get great generation scores, but their reconstruction scores are terrible
Wait, why is that?
because they essentially alter the image to make it fit. You put in a photo of your dog, and the model gives you back a high-quality photo, but of a slightly different dog.
Oh, which is completely useless.
Yeah.
If you are trying to do precise image editing or data compression, you need the same dog back.
Exactly. Unified Latents keeps the reconstructed image incredibly faithful to the original imprint.
And it isn't just static images they tested, right? They tried this on video, too.
They did. On the Kinetic 600 dataset, which is for video generation, they hit a state-of-the-art FVD, or fresh-it video distance, of 1.3.
Wow, 1.3 for video.
Yeah, this proves the whole framework isn't just some quirk of 2D images. It scales perfectly to time-based sequential data as well.
I was actually looking at some of the visual examples they described in the source material. They mentioned prompts like a frog in a sweater and a panda surfing.
Gotta love the classic AI benchmark.
Right. But the real point was, when they scaled this framework up to text-to-image models, the alignment was fantastic.
You mean how well the image matches the text prompt?
Exactly. It achieved better CLIP scores than standard pixel-based diffusion models.
And I think that leads perfectly into the ablation section of the paper.
The ablations, those are the experiments where they purposefully break parts of the model to see why they work, right?
Exactly. And this part was fascinating to me because it really proved their theories.
This is where they test the whole Goldilocks theory on the bitrate.
Yeah, they found that model size absolutely dictates what you can do. Small AI models desperately need low bitrate latents.
Because they just can't process the density.
Right, they simply cannot handle too much information. If you feed a small parameter model a highly complex blueprint, it chokes. It can't learn it.
But the large models,
Large models are much less sensitive to the bitrate. You can feed them those high-info latents, and they handle it just fine, producing amazing detail.
so it really confirms that the packing problem totally depends on the size of the suitcase, or rather the size of the brain you're unpacking it with.
That is exactly what it proves.
And what about that fixed noise in the encoder we talked about earlier? What happens if they change that number?
They tried that. They tried using very little noise. A parameter called lambda, they set it to 10.
And what happened?
Complete failure. The prior couldn't model the bitrate accurately at all.
Really?
Yeah, it turns out that specific fixed noise level they chose, where lambda equals 5, is literally a Goldilocks zone.
Not too hot, not too cold.
Exactly. It provides just enough noise to smooth out the distribution so the prior can learn easily, but not so much noise that you start losing the core data of the image.
It is amazing how specific these numbers get in machine learning. Like 5 is absolute magic and 10 is a complete disaster.
It really highlights how delicate the balance is in this high-dimensional math. They also ran comparisons against standard VAEs.
How did those hold up?
Well, standard VAEs that use normal priors, they require really high bitrates to look good. And as we know, that makes them incredibly hard to generate from later. Unified Latents completely sidesteps this by co-training that diffusion prior we discussed.
Okay, so this all sounds amazing, but naturally there has to be a catch. We are getting better quality, way better efficiency in training, perfectly faithful reconstruction. What is the cost here?
The main cost is time during the actual generation phase.
Ah, okay.
Remember I said they use a diffusion decoder instead of a typical Jan decoder?
To elucidate the fine details.
Well, diffusion models are inherently slower. They require multiple iterative steps to gradually denoise the latent back into an image.
Whereas a Jan decoder is usually just one shot, boom, here's the image.
Exactly. So while Unified Latents gives you noticeably better quality and a much more stable brain for the AI, the actual act of decoding that final image takes more computational time. So it's smarter, but a bit slower to actually speak its thoughts.
For now, yes. But the authors suggest this is a very worthy trade-off for the unprecedented control and quality it gives you.
Speaking of the future, where does this research go next? The paper briefly mentions scaling laws.
This is honestly the most exciting part for the industry at large. Because they have finally made the latent bytrait interpretable and tunable with those volume knobs, they suggest we could establish concrete laws for latents.
Like physics laws.
Sort of. Like an engineer could say, if I have exactly X amount of compute budget, I should use exactly Y bytrait for my latents to get the mathematical maximum quality.
So no more guessing and checking.
None. True optimization based on math, not intuition. And they dropped a massive hint right at the end of the paper. This framework isn't just restricted to images.
Oh, what else could it do?
It could theoretically be used to compress discrete data, like text.
Compressing text into latents.
Yes. Imagine compressing an entire paragraph, not into a text summary of fewer words, but into a latent thought.
A latent thought. Yeah, a dense mathematical representation of the actual meaning using this exact unified latents framework and then having a diffusion model generate new text directly from that thought.
Wow, that is mind-bending.
It really is. It bridges the gap between the continuous world of images and the discrete world of language.
Okay, so to recap all this before we close out today,
Yeah.
Unified Latents solves the fundamental packing problem of generative AI.
Right.
It replaces the blind guesswork of VAEs with a structured trio, an encoder, a prior, and a decoder that actually work together in harmony.
Yes.
It uses fixed noise to keep the math stable, and a separate Stage 2 base model to make sure the final results look good to human eyes.
Perfect summary. And it proves that if you treat image generation as a precise, bit-measured communication channel, you can absolutely beat the current state of the art.
Here's a thought I want to leave you with as you go about your day. If unified latents allow us to treat generation as a precise channel, like you said, could we soon see this logic completely take over large language models?
It is entirely possible.
Are we moving toward a world where AI doesn't even read words anymore, but strictly manipulates these latent thoughts that are far denser and more efficient than human language could ever hope to be?
That is exactly the question the next generation of AI models will have to answer.
Thank you so much for tuning in to this deep dive on unified latents.
It was a pleasure exploring this with you.
If you enjoyed this conversation, please subscribe for more deep dives into the papers and concepts shaping our future. We will see you next time.